Hook plus backstory. Imagine sending a probe to the very edge of the universe. 46 billion light years in one direction, a distance that light takes longer to travel than our planet has existed. The probe flies for billions of years. It reaches the edge of all that exists. It turns around, it flies back, and returns in a week. This is not science fiction. It is a consequence of equations that Albert Einstein wrote more than a century ago. Equations that still defy intuition, even for professional physicists. Equations that turn time, the most unshakable constant of our existence, into plasticine. And today we will examine how this is possible. The year is 1915. Europe is drowning in the trench mud of the First World War. Empires are collapsing. Millions are dying for scraps of land that are worthless. Meanwhile, in Berlin, a 36-year-old physicist with unruly hair is completing a decade of work. He does not know that in a few years he will become the most recognizable scientist in history. He is simply trying to understand how gravity works. Albert Einstein publishes his general theory of relativity, a set of equations that turns everything humanity knew about space, time, and the very fabric of reality upside down. Newton considered gravity to be a force, an invisible hand that pulls apples to the ground and planets to the stars. Einstein showed that gravity does not exist as a force, there is only curvature. Massive objects bend space-time, just as a bowling ball bends a stretched sheet, and everything that moves nearby simply rolls into this dent. But that wasn't the strangest thing. Einstein discovered that time is not a river flowing at the same speed for everyone. Time is a local phenomenon. It flows differently depending on where you are and how much space is curved around you. The deeper you dive into the gravitational well, the slower your clock ticks. For you, nothing changes. A second remains a second. But for an observer watching you from afar, you seem to freeze. You move in slow motion. You age more slowly. This is called gravitational time dilation, and it is not a hypothesis. It is a measured, confirmed fact that is used every day. GPS satellites orbiting the Earth run faster than ground-based clocks. By 38 microseconds per day, it seems insignificant. But without correcting for this difference, your navigator would be off by 10 kilometers every day. Every time you plot a route to the nearest coffee shop, you're using the theory of relativity. Atomic clocks carried on aeroplanes lag behind those on the ground. This was measured back in 1971 in the Herfel and Keating experiment. The difference was nanoseconds, but it was there, exactly as Einstein had predicted half a century earlier. Even the core of our planet, just 6,000 kilometers beneath our feet, is younger than its surface. Over the 4.5 billion years of Earth's existence, a difference of 2.5 years has accumulated. The core literally lags behind in time because it is deeper in the gravitational well. But all this is child's play. Microseconds, nanoseconds, years stretched out over billions of years. To see a real slowdown in time, one that can be used, you need something more serious than Earth's gravity. We need an object that distorts space-time not like a bowling ball, but like a black hole in the very fabric of reality. Mechanics plus mission concept. A black hole is not a hole. It is a corpse. The remains of a star that lost the war against its own gravity. When a massive star, 8, 10, 20 times heavier than the Sun, exhausts its fuel, it can no longer resist. The thermonuclear fire in its heart goes out, and trillions upon trillions of tons of matter collapse inward. In a fraction of a second, a collapse occurs. The substance compresses to such a density that the space-time around it does not simply bend, it tears. An event horizon is formed, an invisible boundary from which nothing can escape, not even light, not even information, not even hope. Inside is singularity, a point where density tends towards infinity and the known laws of physics cease to apply. No one knows what happens there. Perhaps we will never know, but we don't need to go inside, we need to be nearby. Because near the event horizon, time slows down so much that seconds turn into years. Consider this formula. Delta t dash equals delta t multiplied by the square root of 1 minus the ratio of the Schwarzschild radius to the distance. Dry symbols. But behind them lies something unimaginable. The Schwarzschild radius is the size of the event horizon For a black hole with the mass of the Sun, it is only 3 kilometers. 3 kilometers, and the mass of an entire star is locked inside. The closer you get to this boundary, the more your time slows down. At a distance of 10 Schwarzschild radii, the effect is barely noticeable. At a distance of 2 radii, time flows twice as slowly, and at the horizon itself, time stops completely, forever. To an outside observer, you freeze on the edge of eternity. Light stretches out from you into infinity. You redden, fade and disappear, but never cross the line. For you, it's nothing special. You keep falling. A second remains a second, and only then, inside the horizon, do you realize there is no way out. But what if you don't fall? What if you hang there? There is an object near which 1 minute of your time equals 26 years on Earth. It is called TON 618, and it is real. TON 618 is a quasar, a supermassive black hole at the center of a distant galaxy, devouring matter with such ferocity that it shines brighter than 140 trillion suns. One of the brightest objects in the universe. Its mass is 66 billion suns. That's more than all the stars in the Milky Way combined. If you put every star in our galaxy, and there are about 200 billion of them, in one pile, TON 618 would still outweigh it. The event horizon of this monster is 1,300 astronomical units in diameter. 1 astronomical unit is the distance from Earth to the Sun. TON 618 could swallow our entire solar system, including Neptune's orbit, and still have room to spare. A ray of light crosses her shadow in a few weeks, and it is here that time becomes a tool. Imagine a mission, not today's mission, we don't have the technology, but one that is theoretically possible, physically feasible. The spacecraft reaches the vicinity of a supermassive black hole. Not TON 618, it's too far away, 10 billion light-years from us, but something similar. Massive enough for time dilation to be monstrous, and large enough for tidal forces not to tear the ship apart. This is an important point. In small black holes, stellar masses, gravity changes so dramatically that the difference between your feet and your head can be thousands of G. You will be stretched into spaghetti long before you reach the event horizon. This is called spaghettification. The term is funny, the process is not. But with supermassive black holes, the event horizon is so vast that the gravitational gradient on it is almost imperceptible. You could cross the boundary and not even realize it. At some point, the way back would simply cease to exist. So, the ship takes up position. Not on the horizon, that would be suicide, but close enough. Let's say, at a distance where the time dilation factor is 1 in a million. 1 second on the ship is 1,000,000 seconds outside. 1 hour is 114 years. 1 day is almost 3,000 years. A probe is launched from the ship, unmanned, autonomous, capable of flying for billions of years without human intervention. The probe goes into the abyss, away from the black hole, away from the ship, to the very edge of the observable universe, where the cosmic event horizon is located. Not to be confused with the black hole horizon, that's different. The cosmic event horizon is the boundary beyond which galaxies are moving away from us faster than the speed of light. Yes, this is possible. Space itself is expanding, and the speed of light does not apply to this. Currently, this horizon is approximately 16 billion light-years from Earth, but the observable universe extends further, 46.5 billion light-years. We see light from objects that emitted it billions of years ago, when they were closer. Since then, they have drifted beyond the horizon. We see their ghosts, but we will never be able to reach them. The probe is flying towards this boundary. It is collecting data. It is photographing what no human eye has ever seen. It is measuring relic radiation, the echo of the Big Bang, with a precision that is impossible from Earth. It is searching for answers to questions we have not yet learned to ask. Billions of years pass, for the probe, for the universe. Stars are born and die. Galaxies collide and merge. Civilizations, if they exist anywhere, flourish and perish. The sun itself will turn into a red giant, engulf Mercury, Venus, and possibly Earth, before collapsing into a white dwarf. And a week passes on the ship. The probe returns, with data on what the edge of all existence looks like, with answers about the nature of dark energy, with evidence, or refutation, of the existence of other universes beyond our own. The ship's crew undocks from the black hole's orbit. They return to where Earth once was and discover what? It depends on how long they spent at the horizon and on whether humanity survived. But they return with an answer to the question that has tormented us since the first human looked up at the stars. What lies beyond the edge? It sounds like science fiction, but physics does not prohibit it. Every equation adds up. Every law is obeyed. The problem lies elsewhere. Obstacles plus epilogue. Problem number 1. Distance. The closest known black hole is called Gaia BH1. It was discovered quite recently in 2022. It is located in the constellation Ophiuchus, only 1,560 light-years from Earth. By cosmic standards, it is in the neighbouring yard. But this is a black hole of stellar mass, only 10 solar masses. Its event horizon is about 30 kilometres in diameter. Time slows down significantly near it, but tidal forces will tear any ship apart long before it gets close enough. We need a supermassive black hole, one where we can safely hover at the horizon. The closest supermassive black hole, Sagittarius A star, is located at the centre of our galaxy, 26,000 light-years away, 4 million solar masses. That's better, but still not enough for truly extreme time dilation. And black holes of class TON 618, the ones where a minute equals decades, are billions of light-years away from us. Voyager 1, the fastest and furthest man-made object, travels at a speed of 17 kilometers per second. In 47 years, it has covered a distance of one light day, 25 billion kilometers. Sounds impressive, but to reach Gaia BH at Voyager's speed would take 27 million years. To Sagittarius, a star, 450 million years. A ton is 618 million we accelerate the ship to 1% of the speed of light, which would require energy comparable to the annual consumption of the entire Earth civilization, the journey to the nearest useful black hole would take millions of years. The irony is that the time machine exists, but to get to it, you need time, which we don't have. Problem 2. Survival. Let's say we somehow solved the problem of distance, warp drive, mole tunnels, generations of people replacing each other aboard the Ark ship. It doesn't matter, we made it. Black holes do not hang in the void like lonely monsters. Active black holes are surrounded by accretion disks, rotating funnels of hot matter falling inward. The temperature in these disks reaches millions of degrees. They emit X-rays, gamma rays, and streams of charged particles. Radiation near an active black hole will kill a human being in seconds. Electronics, even faster. Any spacecraft approaching the event horizon of an active quasar will turn into a cloud of ionized vapor long before the time dilation becomes noticeable. There are dormant black holes such as Gaia BH1. They do not actively absorb matter. There are no deadly disks around them, but dormant black holes usually have stellar mass. This means they have deadly tidal forces. Finding a supermassive dormant black hole within reach is like looking for a needle in a haystack the size of a galaxy. Problem 3. Communication. Let us assume that the spacecraft has arrived. Let us assume that it has found a safe position. Let us assume that the probe has been launched and has flown to the edge of the universe. How will the probe find its way back? Over the billions of years that will pass for it, the universe will change beyond recognition. The stars it used for navigation will fade away. Galaxies will shift. The black hole itself may merge with another black hole or evaporate through Hawking radiation, although the latter will take a time incomparable even to the age of the universe. How can a signal be transmitted across billions of light years? Radio waves dissipate, laser beams defocus, gravitational waves, the only type of signal capable of travelling such distances without distortion, require detectors the size of a planet. And even if the signal gets through, what's the point? For the ship's crew, a week will have passed. For the civilization that sent the expedition, an era will have passed. Those who waited for a response will have long since turned to dust. This is the trap of relativistic travel. You can outlive the universe, but the universe will not wait for you. Problem number 4. We don't know what we don't know. General relativity works. It has been verified to 14 decimal places, but it is incompatible with quantum mechanics. And near the event horizon, quantum effects become significant. What happens to information that falls into a black hole? The information paradox remains unsolved. What is inside the singularity? We do not know, and may never be able to find out. Does Hawking radiation exist in practice, or is it just a theoretical construct? It has not been experimentally confirmed. We make plans based on equations that may be incomplete. We draw maps of territories where no one has ever been. This does not mean that the theory is incorrect. It means that reality may turn out to be more complex. And yet, 100 years ago, the idea of flying to the moon seemed crazy. 50 years ago, interplanetary probes were the stuff of science fiction. 30 years ago, we didn't know of a single planet outside the solar system. Today, more than 5,000 have been discovered. Voyager 1 has been flying for almost half a century. It is the loneliest object ever created by humans, 25 billion kilometers from home. Its signal takes more than 22 hours to reach Earth. Its nuclear batteries have enough energy left to last a few more years. Soon, it will fall silent forever, but it is still transmitting data. It is still telling us about the interstellar environment, the space between stars where no instrument has ever reached before. In 40,000 years, it will pass within 1.5 light years of the star Gliese 445. It will not stop. It will not turn back. It will simply fly by, a silent messenger of a species that may already have disappeared by then, or it will not disappear. In 2015, LIGO detectors recorded gravitational waves for the first time, ripples in space-time caused by the collision of two black holes a billion light-years away. We literally heard monsters collide. Einstein predicted this phenomenon 100 years before we were able to detect it. In the year 2019, the Event Horizon Telescope photographed a black hole. Not its shadow, not an artistic illustration. A real image of an object that is, by definition, invisible. An orange ring of superheated gas surrounding absolute darkness. The first photo in history of something from which there is no return. We are just getting started. The idea of sending a probe to the edge of the universe by slowing down time at a black hole is not a plan. It is a thought experiment, an exercise in what is physically possible but practically unachievable. not achievable at this time. 100 years is nothing in the grand scheme of the universe. 1,000 years is barely a blip. But for humanity it may be enough to learn how to harness fusion energy, to build engines that can propel ships to significant fractions of the speed of light, to find ways to protect ourselves from radiation, to create artificial intelligence capable of managing a mission lasting billions of years, or to discover something we cannot even imagine yet. New physics, new dimensions, new ways of travelling through space that Einstein could not have imagined. The edge of the universe exists. The boundary of all that exists is real. It is 46 billion light-years away from us, and with every second it moves further and further away. We may never get there, but we'll never get there if we stop trying. Space is indifferent to our dreams. It does not wait for us. It does not invite us. It does not promise rewards for bravery, but he doesn't forbid it either. All you need is time and perseverance. And perhaps one day the probe will return in a week with answers to questions we have been asking for millennia.